Hello, everyone. I thought today I would talk about GitHub Codespaces. Geert Heber had gone through some C examples with Codespaces a few presentations ago, but I've been looking at it and I've made some additions to our HDF5 tutorial that makes running HSDS a lot easier. So just to recap, Codespaces are like a virtual machine that you can just start up from your browser. So if you go to GitHub and select Codespaces, you'll have an option to create a new Codespace, I believe. Yeah. So you say new Codespace, and then you can select your repository. So we're using HDF5 tutorial. And actually, the changes I've made aren't in the main branch yet. So it would be the HS setup branch. And you can choose your region. So Europe West, US East, US West, and so on. And it doesn't matter a great deal, but if you know you're going to be accessing some cloud resources that are in a particular geographic region, you'd want to be in that region. So in this case, we're going to be accessing some S3 buckets that are in the West Coast. So I would choose US West. And then machine type, you can select 2 cores, 4 cores, 8 cores, 16 cores. And actually, I think there's some paid options that are 32 cores or GPUs and so on. And if you're going to be using HSDS, you actually, the service will take advantage if you have, say, 4 8 cores. So I would choose, 4 cores is probably quite adequate. And then you do create code space. Now, it takes a while for this Docker image to generate. So I'm going to, just trust me, that if you click that, you'll get a new code space. But I'm going to go to a code space I already have set up and running, which is here. So it's basically the same settings I was showing. And the changes, you can see, if we go to the Explorer view. So dev container are where all the settings that manage your code space environment. And we've added a Docker Compose YAML. So what this does, it defines all the different containers that are part of your environment. So when Geert Heber was doing his presentation, you basically just had this app container. And I've gone through and added these other containers for HSDS. There's the head, DN containers, S container, and so on. And the result is when it starts up, not only do you have your Jupyter environment, you also have HSDS running as part of your code space. So when you start the code space, HSDS will start, and it'll keep running as long as your code space is active. And when you exit, it shuts down. So if we do some of our typical HSDS commands, like hsinfo, you can see that this is HSDS for GitHub Codespaces. It's ready. The endpoint is localhost 5101. Username is VS Code. Your home folder is /home/VS Code. There are 4 DN nodes, and it's been up for 39 minutes. Okay, so basically, you can do anything you would do with a purposefully set up HSDS server. So if I do hsls /home, by default, you will just have this /home/VS Code. It's kind of your pseudo home directory for HSDS. So let's see, let's grab some HDF5 file and then load it into HSDS. So if I go here, I think I have a wget script. Yeah, this guy. So I could run it in the Jupyter, but let me just grab it and run it on the terminal. So I do paste and see allow. So I should say, in this case, I'm running in the browser, but you also have the option to run VS Code and connect to a code space. Let's do wget. So I have this tall.h5. We have all the HDF library tools here. So there's the file. And if I do hsload call.h5/home/VS Code, that gets loaded. And now if I do hs, not h5, but hsls-r home VS Code tall.h5, we see all the same content, but now it's in the HSDS server environment. The storage that HSDS uses, in general, it can be files within your environment, it can be S3 buckets, or it can be Azure blob storage. By default, you'll use data in your CodeSpace environment. And you have, by default, there are 30 gigabytes. Let's see, verify that. So yes, available, used 9 gigabytes, I'm not sure what, and available 21 gigabytes. So, and the files are in here. I can show it. The HSDS data, HSDS test, that's the default bucket. If I say DB, and this guy, okay. So HSDS uses a sharded format. So well, that makes more sense. So things like data sets and groups metadata are stored as JSON, and chunks are stored as binary blobs. That's why when I try to click on 0, 0, that's the first chunk of that data set. It can't display because it's a binary thing. All right. So that's fine if you have the amount of data that you need to use is fairly limited in size. But what happens if you need more than 30 gigabytes? That's where I think this idea of having the code space run in the cloud is really powerful. So let's go to this example, Python NREL NSRDB example. So before I run the notebook, let me just do this from the command line. Yeah. If I do HSLS, so before I did HSLS /home/VS Code /tall.h5, now I'm doing HSLS --bucket s3:// nrel-pds-hsds. Okay, so that's saying don't use the default HSDS POSIX bucket. Use this S3 bucket that is at nrel-pds-hsds. And I happen to know that this bucket is in the US West region. That's why I was saying it's slightly more efficient to choose your VS Codespace to run in the West Coast of North America. And you see there's a bunch of files here. If I do, oops, what happened to my thing? See, there's CONUS. And if I add, I don't have man recovery for this. If I add some more parameters, -h and -v for verbose, yeah, I got an error. What did I do? One second. Pages? Oh, that's hmm. Uh, okay. So yeah, finally. So you see in this folder, the slash nrel slash nsrdb slash conus slash, there are 5 domains, which are the HSDS equivalent of files, and they're each about 12 terabytes. So it's quite, 12 terabytes is quite a bit more than 30 gigabytes, and you'd be hard pressed to, even if you had sufficient disk space, it would take hours to download, or days even, to download all that to your local machine. And there's actually quite a lot of data in the, like here's another command. I can run -r /nrel. If you total up all the files they have, it's close to a petabyte. So this just scrolls on and on, but you can see they're files of 300 gigabytes and 3 gigabytes. And there are a few multi-terabyte files. Here's a 1 terabyte file, and so on. Right. So it's a huge amount of data that is freely available to access. And the only thing is the challenge of being able to read it with a reasonable amount of speed. So let's go to the notebook. So there's just like these tutorial examples, you have this option to use H5Py or H5PyD. So we'll start with not using H5Py, and instead we'll import H5PyD, which is the HSDS Python client, as H5Py. So I don't need to change any of the other code. I just use H5Py, but in this case, H5Py is really a stand-in for H5PyD. Let's run that. And this we saw. So let's use H5Py, actually H5PyD dot file and the /nrel/nsrdb/conus/nsrdb conus 2022.h5. So that was the 15 terabyte size file that we saw flash by earlier. And the bucket is s3://nrel-pds-hsds. So the s3:// is important because it distinguishes that we want to read from an actual S3 bucket rather than our simulated POSIX buckets, which would be part of our 30 gigabyte partition. And this percent time is just a Jupyter Lab hack that shows me the runtime for this command. So that took 54 milliseconds. And now we have a handle to this file. If I say f.attrs version, I'll get this attribute. And we'll see it's version 4.0.0. And you notice the runtime here is actually quite small. That's because by default, when you do the H5PyD file to open, you pull in all the attributes for all the groups up to some fairly high limit. So in this case, we've already read all the attributes in that first request, and they're in memory now, so it's just very efficient to read. If I do list F, I'll see all the members of the root group. These are all data sets. And you'll see there's quite a few data sets here. Let's grab one, the air temperature, because I know what that means. I'm not sure what some of these are, like CLD, press, ACHA, but NROL will have documentation to describe all these. So if we look at the data set, it's two-dimensional, and there are some 105,000 rows and 2,842,719 columns. And the way NREL set up this data, the first dimension is basically a time series for the entire year. The second dimension is an index to these millions of different stations they have geographically dispersed over the continental US. Okay, so if we look at dataset.id.id, it's you can tell we're talking to HSDS because in the library this would be a integer value. Here it's a GUID value, and the shape again is the 105,000 by 2 million. The chunks is 2,000 by 500. So the size of the chunk, so we'll multiply the dimensions of the chunk by the size of the data type, and we'll get 2 million, right? So it's 2 megabyte per chunk, basically. And how many chunks are in the entire data set? Well, take the shape, first dimension of the shape divided by the first dimension of the chunk times the second dimension of the shape divided by the second dimension of the chunk, and that's a typo there. So there are almost 300,000 chunks. So 300,000 times 2 megabytes is roughly 3 gigabytes. So now let's grab some data. Let's say, so far, we've only accessed metadata from this S3 bucket. Now I'm going to take my data set and say, give me all the values for the first dimension, and at this column, 1, 2, 3, 4, 5, 6, 7. I could have typed anything else, but it's fine. And we fetched that in 60 milliseconds. And then, so you think that this is actually accessing 50 chunks because we're cutting through each chunk along that first dimension. And there's 2 megabytes per chunk. So that's 100 megabytes of S3 data that was read to get the NumPy array that was returned by this access. And then if I do time series at min, time series at max, time series at mean, it's kind of useful seeing the range of the data. It's minus 121 to 431 to 173. I think these are in tenths of degrees centigrade, but I'm not sure about that. And we can plot the data. And there we have a nice plot. So you see that at the start of the year, at the end of the year, it was rather colder than in the summertime. And then there's lots of variation, day and night cycles and cold snaps and whatever. Okay. Now, the file we've been talking about actually links to several different HDF5 files. And you can see, if you poke under the covers a little bit, there's in H5PyD, we have a property called layout. And I can see that. So it's another JSON. And the class is called H5D chunked ref indirect. So this is a type of data layout that says the actual data for the data set is somewhere else. And that somewhere else is in this file, s3://nrel-pds-nsrdb/conus/nsrdb _conus_pv_2022. Right. So HSDS is going to read chunks from this file. But where are the chunks? Well, that's what this chunk table is for. The chunk table is a HSDS anonymous dataset, meaning that there's no link path to it. But it's used to store offsets and sizes of each chunk in this file. So remember, there's thousands of chunks, and so this chunk table has to be large enough to store a value for each chunk in the file. And then it turns out that if we go through here, if we iterate through each data set in the domain and do this file URI for layout and then add it to the set, we can see that it's not just one file, there are a bunch of different files, right? So you have one HSDS domain with many data sets, and those data sets, metadata, are pointing to various HDF5 files. And one of the rationales why NREL has set this up is that Amazon has a maximum size limit for an S3 object of 5 terabytes. The total size of all these data sets is pushing 15 terabytes. So this allows them to provide one HSDS domain that contains all this various data, but actually keep the file size of the actual HDF5 files under 5 terabytes. Okay, so let's go all the way back to the top. And remember I was saying that we can flip this from H5Pi to H5PiD or vice versa. So if I set this to true, okay, so now we're going this path. We're importing H5Pi and importing S3FS. S3FS is a Python package that provides what's called a file-like object to H5Pi. It kind of tricks H5Pi library into thinking they're looking at a file when actually they're reading from S3. And we don't do that. And here, I'll open one of these HDF5 files that the HSDS domain was actually pointing to. So that took 600 milliseconds. That was really fast. So, and now let's read an attribute. So it was like speedy quick in H5PiD, and still pretty fast, 1 millisecond to read this. So in that 1 millisecond, our code running H5Pi through S3FS had to make a request to S3, probably several requests, get all the various metadata and bring that back. And again, we can list the contents. That's all the same. No, it shouldn't be the same. Yeah. So here in this file, we only have these 5 data sets. But one of them is air temperature, so this should work. And we got that. So remember I was saying that in the library, dataset IDs are numeric and not goods. So we do this. We see now we have a integer ID. This will all be the same, as is this, as is that, and that. Okay, so now let's read the same column from the data set again. So it took 60 milliseconds in HSDS, and it's going to take quite a bit longer. Okay, so while this is running, let me try to explain what's different about HSDS. Well, remember that we had four what we call data nodes running HSDS. So you have four-way parallelism because you have four processes living in these four data node containers. And secondly, it's using async I/O, meaning that each of these containers is simultaneously doing multiple S3 read requests. So it's roughly 8 running at any one time. So you have 8 times 4 containers. So you have basically 32 read requests at a time. And that is much faster compared to the library, where it has to currently make one request, read one chunk, and then read another chunk, and then another chunk, and so on. So in total, it took 47 seconds to read this. This is probably not the best scenario for using S3FS. Oftentimes, it's quite reasonable in performance. Here, it's a bit of a challenge because you're cutting through so many chunks. It has to read a lot of data from S3 and pull it over to return the desired array. All right, so that's that for example. I've gone through and I've reworked all these Python tutorial examples, and they're all the same way. You can select from H5Py or H5PyD, and it goes through different things and explains the difference between H5Py and H5PyD as they apply, and so on. So if you are new to H5Py or H5PyD, or you're just curious how HSDS works, I think it's quite worthwhile to run through these different examples. I'm planning to return to this Codespace example for future talks. I think it's a very convenient place as we have new features. We can show it through this Codespace, and anyone else who's curious can run their own Codespace and see the exact same code. You avoid all the challenges of having to download packages and get fiddle around with getting things working. So I think it'll be a very useful vehicle for that. All right, that's all I had to talk about for Codespaces this time. Any questions about this, and are there any questions in general that I can help with? So Lori, no questions? Anything on chat?
Nope, nothing in chat.
Okay, I guess I was just too clear in my explanations. So, but anyway, thanks for everyone who attended, and we'll chat next time. Take
Right,
care.
thank you.
Okay, bye bye.
Thank you very much.